probabilities with those, more like, here are possible scenarios. So that's the green part. And as you might expect, as we expect, the socioeconomic variabilities and uncertainties dominate if you think overall. These are in climate called the emissions scenarios. And then the ones in blue, these are this variability, and which then translates to uncertainty, arises because of knowledge gap in the natural sciences. So when I say knowledge gap, this can be gaps in our understanding or gaps in our ability to encode our understanding within software models, whatever it might be. But that's this variability, which is, which I'm calling, or people have been calling, model spread. And again, it's our gap in the understanding of natural sciences. I wanted to highlight the orange part. The orange part is, even if we understood emissions perfectly, carbon dioxide or overall greenhouse gas emissions perfectly, even if we had the perfect scenario, even if we understood the physics and chemistry and biogeochemistry and biology, etc., perfectly for our Earth system models, even then we'd have certain kinds of variability. This is the intrinsic or natural variability of the system, not very dissimilar to what in weather we know as chaos, butterfly effect, the strange attractors, or extreme sensitivity to initial conditions, etc., etc. These are similar entities, except that for a, there is, one could think that in climate, because of longer term, climate is usually solved as a boundary value problem, longer term. So you could think that these things would go away, but turns out they do not. In fact, in the critical phase for about 10, 20, even 30 years, this intrinsic variability, which then translates to what I've been calling irreducible, or some of us have been calling irreducible uncertainty, this is comparable to the trend, and this is also comparable to the overall variability, or this dominates the overall variability. This is hard to design for, plan for, but we have to be resilient to this. And in fact, there are, one issue is, you might say, okay, it just is important here, not there. But remember, most of the decisions and policies that are made are often made in the relatively short time frame, decadal time frame. It's easier for policymakers to understand that time frame, make those decisions. Okay. Now, the thing though is, this irreducible uncertainty grows as you go from, so the top two are temperatures, as you go from global scale to city scale, this component, the irreducible uncertainty component. So here what I'm showing is the irreducible uncertainty and the model spread only. I'm not showing the green part. So this irreducible uncertainty grows. And if you're looking at precipitation, it's even higher. So the top two are temperature, bottom two are precipitation, and look, it even grows. So we have to characterize these kinds of variabilities and uncertainties, but we still have to be resilient to these. Now, the other issue is, and why I call these things convergence of complexity, is what I just told you is an example of complexity in the earth sciences, with an example from climate. So what I've been showing you is, this is from IPCC Intergovernmental Panel on Climate Change. This is part of our work. Why somebody, the PhD student at that time who worked with me on this is Devashish Kumar. It's his work. He, by the way, is also a graduate from IIT Kharagpur, much later than many of us, obviously. But anyway, so then I come to the other kinds of complexity, which are sort of integrated in a sense. So one reason why we care about extremes, these extremes and anomalies in climate or weather happen out of this, out of the spatiotemporal complexity and the changes, the dynamics that go on, these extremes arise. But once these, and they are of course exacerbated by the fact that there are all these human induced components these days. But once these extremes arise, we care more about them because they can spread much more easily than what used to be the case earlier. So if you think about, here is an example how this was from a paper more than a decade ago now in Nature, which talked about the power grid failure in Italy and how that power grid failure quickly cascaded across almost the entire country, and how that impacted communication And then communication failures impacted power grid failure even more, et cetera, et cetera. And the thing is, these things quickly spread or seem to spread from relatively small disturbances, relatively small or at least localized disturbances. They can quickly spread across entire nations, regions, even the world, because we are just so interconnected. So it's not just that extremes may happen in the complexity of our sciences, but it's also that these extremes get in a sense magnified because we are so interconnected. And of course, if you think about power grid getting impacted, communications getting impacted, and vice versa, power grid then impacts water pumps, so water systems get impacted, power grids impact signals and systems, transportation gets impacted, etc. So here is again some of, one of our work. This is by former PhD student Kevin Clark, who is now big director, I understand, at U.S. Department of Transportation lab called Volpe. He works in aviation. So his PhD work looked at flight operations and how a relatively localized fire in an airport or a snowstorm in one part of this country, of the US, can quickly spread and create disturbances in flight patterns across the country. And this is true, of course, for across the globe. I mean, here he looked at the US national airspace system. The other thing to consider is, in addition to the complexities that we have in natural systems and in human engineered systems, we have complexities in social systems. And when we think about climate and weather impacts and climate and weather challenges and what we should be looking for, what kind of models we should be built to get what things right, we have to consider all of them. Now, in the context of social sciences, in the context of considering complexity in social sciences, of course, the idea is that as things spreads across societies, I mean, these days we don't have to think too hard. Even if we think of, let's say, social media and how misinformation spreads, right? So these are all consequences of how connected we have become, in a sense, as society, and how easy, for example, it's for us to form echo chambers across the globe. Anyway, but coming back here, this was Professor Elinor Ostrom. She is the first woman economics Nobel Prize winner. And what she said is how to harness the complexity that we see in social systems and come up with justifiable, measurable, evidence-based action for which you can evaluate the outcomes. So in her case, social systems and what she called biophysical systems, basically the kind of things that we deal with, how they interact. One interesting comment from her work is that one of the best ways for these social systems to evolve and be productive is not complete autocracy and not complete disorganization, but something that she called polycentric management. So management or organizational groups that evolve, maybe even self-organize, and then they interact with each other and they sort of work in teams within the organization, and then they think about both system level objectives as well as the objectives of their own groups. I'm not sure if this is the best example, but when I have thought about Professor Elinor Ostrom's work, one thing that I sometimes think about is Amul. Anyway, so this was from something we published at the United Nations Association of the UK. And what we are trying to say is, when we think about some current situations in certain parts of the world, including sometimes in the country where I am based in right now, there is significant policy myopia that we often encounter, which leads to financial disincentives, engineering stagnation, and outdated best practices. One thing we have been trying to say is, although this seems like a vicious cycle from which we can never get out, in reality, it's not like that. Certain kinds of financial incentives, bond markets maybe even, right? Or certain resilience bonds, things like that, or other kinds of incentives, insurance and so on. Certain kinds of incentives And some transformation in science and engineering can turn the wheel relatively easily, given how it looks, how bad it looks, can turn the wheel in the other direction. So anyway, that's what I've been calling convergence of complexities. It's complex natural systems, so chaos and natural variability in complex, for example, climate systems, same as weather systems also. Then cascading failure in human engineered systems, or even in general in impacted networks. Some of those networks, by the way, may be human impacted, but they may also be natural, such as ecological network. But of course, here we've been talking mostly about lifeline, things like transportation, power grid, etc., or any interconnected systems. And then complexity in social sciences, such as polycentric management. So somehow we have to be able to deal with this in some way. We may not be able to solve this problem entirely. This is a huge problem, but the thing is, we may be able to either go deep into any one of these areas, which is what we often do in academia or in research, but uh, maybe we can also define problems which go traverse a little bit of these interdisciplinary areas, go a little bit in the uh, direction of, we look at, okay, here is a problem in the earth sciences, here is a problem in human engineered systems, here is social systems, how they come together, and now we need to solve it in a way so that we can give rise to something that's, or we can address something that's of huge social significance, global priority. And if you're thinking just from the point of view of climate and weather models, they can maybe feed back into what needs to improve. What questions should we be asking? All right. So just to give an idea then of what do I mean by these incentives, what can happen. So, and this is again a bit different maybe from what we'll hear as part of this overall workshop, but I still wanted to mention this. I think a little bit more of this kind of thing might be great in India, although I know a lot of things are already happening. So the idea here was that we see many cases where there are these, startups, companies, etc. Yes. Okay. Uh, Startup companies, etc., where which are in IT or AI or finance or hedge funds, and more power to them. That's all great. But point is that we do not see that much work in sustainability or areas of social entrepreneurship, social impact. And sometimes things like climate, people have been saying, I mean, people as in United Nations, secretary generals have been saying that climate is the defining challenge of our age. And yet it's very hard to find for our young graduates, whether it's undergraduates or masters or PhDs, where do I work? I want to work in this area. I am convinced, but where? Which company will work? And then, okay, you work somewhere else, and then maybe you find some time on your own to do some climate work, and that feels good. But if you really think something is a defining challenge of our era and something that impacts us and the entire planet, or at least human sustainability in the planet, that's not a way of doing things. That somehow you volunteer some time and do things. So what one of my former PhD students, Evan Kodran, that's him right there, asked me is that we talk about all these assessments, we don't do anything. Can we show that you can build companies in this area of sustainability and climate and still be able to pay bills? So he started, and I was a partner in crime, but it was mainly him. So he started this company called Risk, which is quantifying risk. So that's why RISQ. And long story short, this focused on urban climate risk, took things from climate, sea level rise, other kinds of things, heat waves, flooding, which are fairly uncertain. And I gave you some sense of the uncertainty, but there is also a trend. So we know things are going to happen with variability. We have to consider both the trend without minimizing the uncertainty and come up with resilience solutions that are that take into account, that are sort of risk informed, if you will. So that was the technical part of it. A lot of climate model simulations, a lot of observations, a lot of data driven science, statistical methods, some nonlinear dynamics, some machine learning, all kinds of things embedded there. But that by itself will not make it into a startup company. So the other thing that that eventually happened out of a lot of things, I mean, through various efforts, I mean, dedicated efforts is to identify the market. In cases like this, you have to build the technical solutions even as you are identifying the market. So what is the market here? Urban bond markets. Not a big deal yet in India, I understand that, but in this country, municipality bonds, muni bonds as they're called, are a big deal. So then if something happens in cities, let's say I am a property owner in a city, I'm a large property owner, and the cities get rated by let's say, I mean, from multiple aspects, financial, governance, all kinds of things, infrastructure, and all kinds of things. But let's say they also get rated in terms of climate vulnerabilities. And in cities, people know that there are climate vulnerabilities, they are happening already. But they found it very difficult to find, say, okay, here is how much this vulnerability is, and so on. So rating agencies, people like Moody's, S&P, for example, and bond investors and bond issuers, this is municipality bonds, muni bonds, bond issuers and rating agencies would sometimes talk with each other, and investors would invest. They are not supposed to talk with each other, by the way, bond issuers and rating agencies, but they had no one to turn to. So when risk came and said, we can say what the climate vulnerability is, they said, yes, we would love that. And then the idea is that they said, well, if risk says, for example, that based on the climate vulnerability, your rating either goes up or goes down from, let's say, A to an A plus or B minus, that impacts me as property manager. So now I have incentive to pay some additional tax, or ask my city government to say, yes, please take some tax, but make sure that we are more resilient to climate, because even ignoring longer term climate and all that, I mean, that's important. But even if I don't think that much, at least I need to think about the value of my property, and that is going down. You need to do something. So that creates the financial incentive while creating the scientific and the science and technologies. This was eventually bought by a Fortune 500 company called Intercontinental Exchange. Intercontinental Exchange is a company that that owns the New York Stock Exchange, so it's pretty big. But and they, I mean, risk in a sense is flourishing within that company now. But point is, this is more of an illustration of what is feasible if we can only bring the latest science and technology together with financial incentives. Evan, by the way, published some very interesting papers, including some that got highlighted, I mean, including one that got highlighted in Nature, and he published some in many other things that have been highlighted. So he's a good scientist, but he chose to also do this. And hopefully, this will motivate others, like it has already in my lab, at least, motivated others to go this route. Now, let me quickly talk about the technical aspect. And again, these things we can always check our papers and such. And I'd encourage you to go through those papers through our lab website, sdslab.io, and you'll get much better idea. But I wanted to give a quick sense. So we have been doing some work for a while now on things like how heat waves and cold snaps and those kind of things, so extreme statistics of extreme weather look under climate change. And there the uncertainties are sometimes important to understand. And things like I mean, is the let's say, is the overall shape of the curve of temperature moving in sync with just a shift in global warming, or are there some other changes that are happening to the curve? Those kind of things. So we found that, for example, that there are higher trends along with larger uncertainty and geographic variability in regional warming and heat waves. But we also found, and when I say we, the first author here is Evan Kodra, the person about whom I just mentioned. So this was published Geophysical Research Letters and mentioned as a research highlight in Nature because it was fairly non-intuitive then. This was 2011. It's no longer non-intuitive now. The fact that even though the world is warming, we will have cold snaps less frequently, perhaps, but the ones that do happen may be as intense or even more intense and as long-lasting, potentially more long-lasting because of various underlying physics than what we see now. So that was that paper, and then it was followed up. We've been doing some other things such as, okay, now let's take a look at what this warming means. So for example, it had been hypothesized that differential land sea warming could intensify coastal upwelling. Coastal upwelling is very important for marine processes, marine ecology. So is there any evidence for that, and can we show that with climate model data? So a lot of model simulations, putting it in the form of metrics that stakeholders care about, and then trying to understand a process. Ultimately, that's related to temperature and how that impacts wind vectors and what that means for coastal upwelling. This was published in Nature. The first author was a postdoc called, his name is Daiyue Wang. And all of this ecology work is joined with my colleague here, Tariq Guhier, who is a theoretical ecologist. Sort of as a follow-up to some of the ecology work, this work was by a former PhD student. Tariq is a constant presence in all of my ecology work, or all of our ecology work. This PhD student, her name is Kate Duffy. She graduated already, but one of her lines of work was looking at these are terrestrial ecosystems and how temperature changes might impact the thermal performance of ecosystems. In this case, she was looking at ectotherms, cold-blooded animals, very specifically insects, which are which we think of as pests, but which are foundational in ecology. And what she was saying, what she has been saying is that, look, overall, we have only looked at change. We have looked at how how changes in temperature, mean change in temperature might impact insects. But what we haven't looked at so well is the combination of that change together with the variability or the uncertainty. And when we look at the changes that are happening in mean and in variance, and potentially autocorrelation, but mainly what she found is mean and variance together, that has greater potential of taking the temperatures, for example, outside of the zones in which insects are comfortable. In fact, they may get so uncomfortable so quickly that they may die off. So that was one of the things that what she found was that these kind of changes, they have diverse impacts in different insects and ecosystems which they inhabit. But overall, the probability of extinction goes up in about 90 to 95% of the insects. By the way, one interesting finding here is just summarized through this equation, which all of us understand in some form, which is the average. The average of the behavior is not necessarily the behavior of the average. All right. Looking at these extremes, looking at these uncertainty and these extremes, one other thing that Evan did again is looking at, could we make uncertainties? So typically when we look at climate uncertainties, for example, from models and translate those to what those mean, in this case, let's say uncertainties in precipitation extremes and what those mean for watersheds. Typically, we look at a couple of things. One is what is called skill. How do these models behave in the past? When compared with observations, and one is consensus. In the future, of course, we don't have observations, but then in the future conditions may change. So whatever we found earlier works may not work anymore. And this goes beyond what in data science we call out of sample statistics. It is out of sample statistics plus function drift. And this function drift, it's non-stationarity, but it's not complete non-stationarity. The Earth will not be, or any place in the Earth will not become like Mars or Venus, but it is constrained non-stationarity. Things will change. So under those conditions, so therefore we look at skills, historical skills with observations, but we also look at how models compare with each other. These models have different physics, or not different physics. The core physics is the same, but different parameterizations, different ways to implement the physics. And if they are saying the same thing about something, then we trust it a bit more. Then we try to come up with Bayesian schemes which can combine those, the skills and consensus, etc. So that has been the usual thing. What Evan also said, and this is Evan and somebody else called, Udit Bhatia, along with some others. We also had Snigdhanshu Chatterjee and Stone Chen. Snigdhanshu was at Minnesota, then now he's at UMBC. He's from the Indian Statistical Institute. Udit Bhatia is also a former PhD student. He's now at IIT Gandhinagar. Anyway, so what they said is that in addition to looking at that, can we also look at physics, physics-informed uncertainties? If you're looking at precipitation extremes, there are some mechanistic ways and some ways based which you can find based on correlations, data-driven correlations, and some physics, the combination of which says that if temperature behaves in this some way, if temperature is so much credible, here's what we can understand about precipitation extremes. Can we use that information together with skills and consensus to get better estimates of um, probabilities and uncertainties? By the way, all these probabilities and uncertainties, despite all of them, we can make decisions. So I was saying that, oh, there's all this variability, all this uncertainty, and what do? We have to still become resilient. It may seem at some point like an impossibly hard problem, but I'd like to stress that it's not necessarily the case. And we are not, I mean, especially if you're looking at pragmatic solutions in some cases, or solutions, engineering solutions, even scientific solutions. So here is for the US Department of Energy, we looked at power production at risk. And this risk framing uses the same risk framing that has been used in other studies, even by the IPCC, but it's a significant adaptation. So we look at water stress from both net water availability changes and rising stream temperatures, both of which are important for water that's relevant for power production. We look at vulnerabilities and exposure of these power plants. And then we say, here are the energy security challenges. We look at all of those kinds of uncertainties that I spoke about earlier, right? The initial value ensembles, which we call internal irreducible uncertainty, internal variability, the multiple model scenarios, multiple emissions. And the idea was to say that, look, we care for those kind of situations where the water that we have grows less. So we are talking about scarcer water and warmer water. And question is, in that quadrant of all of these scenarios, do we have some that lie in that quadrant? And those are the ones we have to be careful about. And where they occur, how much they occur, is what we have to become resilient about. So those kind of things then can lead to decisions. This was used by the Department of Energy to invest in water resilient power production technologies. One other thing is, in terms of decision makers, there is often a need to go from the scale at which Earth system models or global climate models, etc., or even weather, weather is much higher resolved than climate models, but even in weather, we need to often go from the scales at which these model simulations arise and then get to the scales at which we have more, at stakeholder relevant scales, if you will, higher resolutions. And typically, in weather, what is used is called model output statistics. In climate, it's called downscaling. There are various ways to do downscaling. There are physics-inspired ways to do physics model-based downscaling, but that is proving incredibly hard to do while maintaining this huge ensemble of Earth system models, because they're computationally expensive. There is data-driven downscaling, many aspects of that. One thing we found is that computer vision kind of approaches may actually improve these data-driven methods. So we had, this is work by Thomas Vandal and others at, jointly with NASA. Thomas Vandal was a PhD student. He goes by TJ. And this was about, how to use computer vision in the context of uncertainty. This was an award-winning paper at ACM KDD. It was mentioned in Nature Perspectives as one of 4 lines of work in broadly machine learning and Earth systems, or deep learning and process understanding combined in the context of Earth systems. And then also, TJ himself looked at how to deal with uncertainties, especially when these uncertainties are not Gaussian. This was, again, KDD 2018 paper. We have also looked at things like explainability in the context of deep learning. This is explainability, I should add. This is not explainability which is a fundamental theoretical development in explainability in deep learning. I mean, there could be those kinds of work, there are those kinds of work. This is not that. This is more explainability in the context of the science and engineering we're trying to understand. So what we are saying is that now that we have these deep learning, these CNN kind of approaches, this ocean of data that we have from the oceans, from the seas and the oceans across the world. So typically we have dealt with them through indices. This is an El Nino index, and we look at certain things like temperature or pressure difference from here to here, and that forms an index. And then we relate that index to, let's say, things like regional hydrology, such as river flows around the world, which we know that these things have significant impact. But now that we have the kind of data-driven models, the machine learning, deep learning, and the computer vision kind of approaches that we have, do we need to do all that? Or can we look at all of these data sets together and see what impacts they have on these systems, in this case, regional hydrology, which in turn may give us back some insights on the El Nino kind of processes itself. So climate process, hydrologic process with deep learning. Now, the explainability comes in because we just go back. Once we have found something, we go back just through create saliency maps kind of things for what we have found. What they give us is which part of the ocean is triggered. Let's say if there is some variability in the Amazon or the Congo, which part of the ocean is potentially sort of relates to that, at least in a correlation sense, if not full causality right now. Okay, so I was saying that Evan's work inspired several of our students. So this is Kate. I was talking about Kate Duffy. This is TJ Thomas Vandal, and they started a new, they launched a new startup called Zeus AI. Zeus as in the Greek god. The equivalent in India would either be Indra or Dyaspiter. But anyway, so Zeus was the head god in the pantheon of the Greek gods. He was responsible for weather. What their startup does is look at weather modeling with AI, whether it's through data assimilation schemes in weather models, whether it's through post-processing, but it's basically weather forecasting with AI, and they're also building foundation models now for weather and climate. But their idea is to do that to inform renewable energy sector. So solar insolation, wind vectors, that's the kind of thing that they have been focusing on. Recently, they have also looked at, started to look at heat waves in urban settings. So urban policymakers also become one kind of, but mainly it's the stakeholders in renewable energy sector. That's what they are mostly focused on, interested in. And this is a startup which has got grant funding from NASA, SBIR program, Small Business Innovation Research, and then also from DOE, Department of Energy. By the way, one thing I did want to mention is both for risk, which has been RISQ risk, the other company, Evans company, which has been successfully sold off, and this one, so far at least, risk did not take any money from venture capitalists, zero, because we did not want. I mean, one thing is people talk about equity dilution, and it's important, but we also did not want scope dilution. We did not want somebody to say, oh, hey, there is immediate ROI if you do weather rather than climate in that other company in risk. Or why even do weather or climate? You guys are good data scientists. Let's go to the hedge fund market. I mean, nothing against hedge fund market, nothing against weather. In fact, this company is about weather. It's just that company we wanted to focus on climate. So we did not want scope dilution. So that's one reason. But these grant funding mechanisms that exist in the US across different agencies, these are called SBIR programs, Small Business Innovation Research. I think I know that there are some similar things happening in India now, and I hope that more and more of these things will come up to encourage students, postdocs, faculty to think of. Yeah, I can hear you now. It's still garbled, but go ahead.
This weather forecast satellites. So for what phenomena is satellite particularly useful? For precipitation, for temperature?
Yes. So in this case, both. So one is things like solar insolation. In the case of Zeus AI, we have used it for many different things. But in the case of Zeus AI, they're interested in, yes, temperature, incoming solar insolation, those kind of things that matter for the solar industry, and also wind vectors that matter for the renewable wind kind of industry. But yes, we have looked at temperature and we have looked at precipitation. I'll give you one other example at some point.
So for example, for precipitation, it's the, because usually one uses radar to make short-term predictions, etc. But you're saying looking at satellite data also you can say meaningful predictions about rainfall, etc.
Meaningful prediction. Yeah, I mean, so satellites, there are pros and cons. So most of the interesting new developments that are happening right now in the context of, let's say, certain kinds of precipitation prediction, especially short-term precipitation nowcasting, is happening with radar data.
Right.
So you have seen some of these deep generative models of radar and then physics guided models. I'll talk a little bit about those, but not so much satellites. There are still issues, if especially if you're thinking of short-term precipitation forecasting. There are people who are looking at that. We have been looking at that. Is, I would say, still work in progress. Satellite data has been used. Uh, in the context of quantitative precipitation estimation, satellite data is often used, has been used for a long time now. And also in the context of, in some parts of the world, you just may not have radar data or any other observations for that matter. And only thing you have is, is satellite data. So you have to do the best you can. But yeah, there are pros and cons. So we can talk about that. But
But
okay.
you
So
also mentioned, sorry, you also mentioned the wind setting. So you're saying satellite information is actually useful in predicting wind speeds?
I cannot hear very well. I mentioned,
Just one second.
yeah,
So, is that better?
a little bit better. Yeah.
So I was going to say, you're saying also for predicting wind trends, satellite information is useful. Is that right?
That's what they're finding. Yes. So they are finding for solar insolation and temperature and wind. ZSAI is focusing on that. Yes. It's very interesting, the kind of things they're doing. And they have some of their results are publicly available. Some of their results they have published also, including in venues like ACM, KDD. So absolutely. And I'll be happy to point you to some of their work.
One quick question is I'm curious about these satellite pictures and all that. People training on the whole period to different exact features first and then do the training. You know, that.
I cannot, again, it's coming, I'm very sorry, but it's coming across as very garbled.
So my question to you is, when we use satellite information to train deep learning networks, do we use a complete satellite image as input, because one is for the exact features, and then use it for training? Your answer
You
on
know,
that?
what could work maybe better, because I'm not hearing it fully well, is let me go through the slides, and if you could please type your question in the chat window, that might be better. Then I'll repeat that question that I see in the chat window after I'm done with my slides, and then I can answer those. I think that may work better, simply because I'm not being able to hear. It's coming across as very garbled. I'm very sorry, but I don't know why this is happening.
Yeah.
Sorry about that. Anyway, let me, so if you could please type your question in the chat window, I'll try and answer them after I. Okay, thank you so much. So, okay, so going from here, okay, so now, okay, so these are weather, climate. Now, how does that impact communities? This is, for example, as we were looking at the London Metro, and London Metro is one of the most complex, urban rail metro systems in the world and has been there for some of the longest times. So we are looking at resilience of this metro to flood events. And when I say resilience, both in terms of, the fragility of this, but also in terms of recovery potential. So in the left, we are using network science, network methods, network optimization network science, complex network science methods and optimization to see how the failure curve can occur and then how we can recover once failure has happened. By the way, talking about networks in the context of urban rail, some of you may still remember that in the recent, just before actually the recent Paris Olympics, there was there was an attempt to sabotage the France's high-speed rail network, and the French Prime Minister, I think, was the person who made a comment like, "These people seem to have a good understanding of networks." And some of these network science approaches, together with complex network topology and dynamics of this network, this is work by Professor Udit Bhatia, now a former PhD, as I was saying, former PhD student, which looks at how ecological systems post-damage can be recovered. So if you're thinking of food web, ecological network, here he was looking at plant pollinator networks. So, around the world, how these networks can be, once damaged, once perturbed, how these can be recovered, whether it's through introduction of species or through other means, so that you can balance various things related and strength of these networks. So they have broad implications across these systems. And this was probably my first paper, at least in a serious biology journal, but just because from the ecology side. All right. The other thing is these kind of things have impact on installations and facilities. So whether it's Department of Defense facilities, in this case, the picture is of a naval submarine base, or whether it's public sector facilities such as airports, seaports, or whether it's private sector such as warehouses and factories, etc. The idea is that installations are dependent on not just the systems that exist within, but also the ecosystem that supports the installation. So, and a base is dependent on what happens within the base, or all the systems and assets that are within the base, but also depend on power grids and transportation outside. So resilience of that depends on all of those, and how to think of that even through certain approaches. So this is a pending patent that we have. It is our third, well, this is a pending patent, but it is our third patent submissions. The other two patents relate to climate uncertainties and risks, and infrastructural network resilience, broadly speaking. All right, so now let me quickly go through a presentation that I did for the mayor of Boston. Her name is Michelle Yu, and the governor of Massachusetts, so her name is Maura Healey. So this would be like, I don't know, the equivalent in India would be mayor of a capital city, and the chief minister of a state, I guess. So anyway, so they're interested in what AI can do for providing solutions to many different areas, and what I was showing is what AI can do for broadly climate and sustainability. I'll skip some of those, but the kind of things that I'm leading here, one of the things I'm leading here, I should say, is this AI forecast, AI for climate and sustainability. And the four pillars, if you will. One is foundational and translational research. This is Kate Duffy, by the way, getting an award for her paper. This is our KDD award, etc. And a lot of press and all those things, but also hopefully some serious deep research in both climate, weather, as well as data-driven science, computer science, and bringing process-guided and data-driven systems together. Entrepreneurship and community outreach. So the way I have been defining entrepreneurship is not just startups, about which I spoke. And it's good sometimes, in climate, weather, we don't have the Wall Street Journal reporting our work too often. So it's good when they do. New York Times and others report our work sometimes. But anyway, so but the thing is that I also define under the city of Boston, work with the town of Brookline, Massachusetts, work with national climate assessments here, and of course, a lot of our work are cited in IPCC and so on. So that kind of stuff. So community outreach, broadly speaking. Zeus AI calls its AI platform for the planet. So maybe it's from neighborhood scale to planet scale, in terms of the vision, at least. And then education and workforce. So a lot of things that we do there, including global education, things like that. By the way, these pictures are from last year when we went as a lab, not just me. So I go and that's usually not, that's fine, not a big deal. But I was very proud to be able to take all my students, or many of my students and postdocs from our lab, at a United Nations workshop on disaster risks and infrastructure resilience. This was last year. And there were attendees, by the way, from India and from across the world. And then building partnerships and relationships, corporate relations. So, for example, here, as talking about, this picture is about a NASA-funded project that we have, where we are working with Tennessee Valley Authority to try and help bring weather forecasts in the context of river management, flood forecasting. The TVA region, the Appalachia region here, Kentucky, Tennessee, has seen a lot of floods, a lot of loss of lives. Question is, can AI and physics embedded AI help in these areas? This is in the short-term precipitation forecasting scale. This is a NASA-funded project. TVA, by the way, Tennessee Valley Authority, is what, in a sense, inspired in India, Damodar Valley Corporation. I grew up in a place called Durgapur, not too far from Kolkata, and that's where we had a lot of DVC activities, Damodar Valley Corporation, going on. So I had heard about TVA, and it is great to be able to work for them. So the kinds of things we have done. So, city of Boston, we have looked at climate ready Boston reports and contributed to, this was one of 4 things that the climate ready Boston folks looked at. Uh, we looked at extreme temperatures. They looked at three other things like storms, precipitation, etc. But we looked at extreme temperatures. This is Evan Kodra, who was my former PhD student. At that time, he had started his company. And this is a colleague here at Northeastern at the intersection of social science and engineering. Then we also looked at the town of Brookline, Massachusetts here, which is close, which is basically greater Boston. And the work that we did from the Sustainability and Data Sciences Lab through the American Geophysical Union, that was used in their vulnerability assessment report, and it was acknowledged as such. This is the TVA example that I was mentioning. So what we found, by the way, is that in the short term rainfall, extreme rainfall prediction, which is very important, by the way, for flash floods. What we found is that a physics embedded hybrid physics AI, a physics embedded machine learning system. So this is from the same genre as Google DeepMind. They came up in 2019, I believe, with a paper called Deep Generative Models of Radars. So this is generative AI. And this was published in Nature, Mother Nature, no less. And then in 2023, I believe, or no, Google's paper came out, I think, in 2021, if I remember correctly. In 2023, there was this paper, that the dates may be wrong, by this group in Tsinghua and UC Berkeley. UC Berkeley included Professor Michael I. Jordan, who is one of the most famous computer scientists in the world, works in machine learning. The most famous computer scientist, Science Magazine called him, but also the second most famous, Michael Jordan, I guess. So anyway, so they came up with this hybrid physics AI models where they embedded certain kinds of physics, such as continuity equation, basic physics, mass balance, but into the architecture of the deep generative model. And these kind of things, when we started to implement that and understand what it means for the TVA, this is one of my current PhD students, Pooja Dash. So what she found is that, look, we can beat what they were using, which is a data assimilation based physics based model system, which is one of the state of the art models. These things beat that, and they beat standard strawmen such as persistence and advection. So this is very interesting. And what the TVA has said now is that they would like to test this implementation in their operational system, which I think is a big deal. We do our research, we publish our research, we are very interested, and especially if we get something in Mother Nature or some Nature journal or PNAS, we are very excited, and fine, we should be. But I think where the rubber meets the road is if some agencies says that, okay, or some, whatever it is, companies or whatever, if there is some difference in the real world, at least that's where I have been evolving a little bit. Can we make even a small difference? This is very satisfying for us that they have said that they will test it on their operational system. That's the first step. This, by the way, talks about what will happen in the Boston area. This is a 1 in 100-year flood, which rainfall event, which lasts for 24 hours. But towards the end of this century, major parts of Boston that was reclaimed from the ocean, unless we are careful, will have to yield back in some way or the other, especially during these heavy floods. All right, and then we have been working in Boston with Boston's Logan Airport. I was telling you about the US DoD installation kind of work that is part of a significant funded project that we have. But as part of that, we're looking at various proxies, including airports, including urban transit systems around the world. So see, this is Boston, New York, Paris. We have also looked at Delhi, Shanghai, etc., London, of course, and how these systems fail and how the systems can recover and what can be done for more, graceful degradation of functionality and effective recovery. And incidentally, we found, and this is based on real card swipe data. This is New York MTA, the New York Mass Transit after Hurricane Sandy in 2012. And if you think of the recovery post Hurricane Sandy, so Hurricane Sandy happened, there was no traffic, but then at some point the system gradually recovered back. I mean, these stations recovered and people came back. And if you look at that recovery process, the total loss in revenue during this recovery was $124 million, right? Let me run it again, sorry. Was $124 million, the total loss in revenue during this recovery process. Recovery processes, are often fairly disorganized and ad hoc. What we are saying is that even to a first order, if an organizing principle based on data-driven science, network science could be put here, and that's what we showed, then this 124 million could have been reduced to half that amount. So that's significant in terms of revenue. So I just wanted to end with acknowledging all our, many of my, I wouldn't say all, many of my students, postdocs, etc. And, and also this is the group, we went to the United Nations. These are the, like Professor PPC said, very indebted to all the places where I've been, including, my learning experience in the industry and in a government funded national lab. So one of the things that we have been working on across the world actually is looking at things like what climate means for adaptation, such as managing the unavoidable, and mitigation, which has been called avoiding the unmanageable, what it means for resources, hazards, population growth, and ultimately to emissions. This was something that was originally, this was a climate war game that was initially organized by Center for New American Security. And I have sort of tried to translate these two tools to learning tools in pedagogy, if you will. One interesting thing here is that if you think of Human Development Index and per capita emissions of nations, so this is how well we are doing, and this is how much emissions, greenhouse gas emissions, we are, comes out because of that. And remember, these do not count the offshoring emissions. So for example, something is produced in India, but is used in the US, is that the emissions are counted as if they happen in India alone. So with all those caveats though, here is where the world average is in gray. Here is where, the US is, where I'm currently based. Here is where Norway is. So there are countries in the world which are doing better in terms of Human Development Index, let's say, than the US, but with much less per capita emissions. And there are some other countries right around. I mean, this is UK, this is Japan, there are some other, other Scandinavian countries, etc. There are some countries which are doing much worse. So this is Qatar, much less Human Development Index, but much more emissions. Even Singapore emissions is very high, although Human Development Index is, of course, very high as well. But then we come to the sort of middle tier countries in terms of Human Development Index. China is here, Malaysia, Turkey, Ukraine, Brazil. And then we get to Indonesia, where the Human Development Index is here, per capita emissions is low. This is where India is, this is where Pakistan is, this is where, this shows Ethiopia, this is where Congo is somewhere here, Tanzania is somewhere here. And, so question for these nations is, first of all, there is, when we think about emissions in emerging economies, it's incredibly challenging because it's, of course, we cannot say that you cannot grow, you cannot get to higher development index. The question then becomes, how do you grow? Do you grow like this, the pathway from here, or even the pathway that here, right? Do we learn from experience and grow, but grow the pathway like here, that maybe Scandinavian countries have done, that we get cleaner energy, better energy, lower per capita emissions while developing the Human Development Index. This is one thing I've been studying with, and taking students around the world and doing things. We are now funded by Indonesia, government of Indonesia. We've been working with Brazil, Tanzania. I've been to Peru, so all of these places with a strong focus on emerging economies, where I take, and also I take undergraduate students to these parts of the world together with my own PhD students. So thank you very much. If there are questions, I am happy to answer them. Hello? Hello? Can you still hear me?
I think
Okay.
they are muted on that side.
Okay.
Unless they unmute, we cannot hear.
Okay, but now I can hear. Oh, this is Professor.
You are hearing me.
Yeah, I'm hearing you just fine. Yeah. Okay. But what came from the room was a bit garbled, but that's okay.
Yeah. Sandeep, you all are muted.
Can you hear me now?
Yeah, now better. Yeah.
Yes. So I don't know if you have any questions. I mean, I know that I did not just focus on the science here. That was by design. I mean, I've been giving talks about, the science and the engineering and the models and this. These are embedded there, and I'd encourage you to look at, these basically our lab website right here, sdslab.io, and of course Google Scholar and things like that. But I wanted to give a little bit broader feel for the kind of thinking that's going on and what we are doing, and hopefully, what one thing that we did in terms of entrepreneurship, and whether it's community-based efforts, whether it's private sector startups, how that then inspires others. And also in some of our recent research as well, how we are working with various agencies, mission-driven agencies, and other such organizations to actually try and embed some of our research into the real world, if you will.
What is your current work with the monsoon mission, or is it over?
No, it's going on. So with monsoon mission, this is led by IIT Bombay, somebody called Professor Vishal Dikshit, and then there is IIT Gandhinagar, Udit Bhatia, there is IIT Madras, Arun Tangirala, and yeah, it's a project funded by Monsoon Mission. The idea there is to build modules for the models that India's Monsoon Mission has, which so modules that can both work inside these models. So these are AI-based systems that can improve parameterizations. So one of the things in these weather or climate or let's say decadal scale or seasonal to sub-seasonal to seasonal scale, any of these models, is that the basic physics is sort of understood, right? I mean, Newtonian physics is Newtonian physics. We have the Navier-Stokes equations, and those kind of things for fluids. And when it's on the Earth surface, we have Navier-Stokes with the Coriolis force because of Earth's rotation. Basic things are similar, but then there are various. I mean, just with those basic things, we won't be able to understand things like hurricanes or precipitation extremes, even heat waves to some extent. So there are a lot of parameterizations that goes into these models, and especially those parameterizations need to be very useful when we go to subgrid scales, higher resolution. So that's what we are looking at. One way to look at this subgrid scale is post-process the models. We have the model simulations, then do these computer vision approaches, other approaches to see if we can get better insights, enhanced insight. But other ways to go inside these models themselves and see if we can improve parameterizations within the models with AI, assuming we have other data sets and so on. So
the computer vision models are all CNN,
in this case,
CNN.
Yes, in this case, for our case, I mean, people are using various things. In our case so far, all CNN. But here we are saying that, could we use these models? I mean, could we use different kinds of machine learning models to, let's say, get, first of all, from a higher resolution model to from a lower resolution model output to a higher resolution model output at that subgrid scale? Can we get better with projections, and can they sort of, whatever we learn from certain kinds of data, would they generalize? So that is one focus. And the other focus is post-processing module using things like complex networks. And can we get better insights on different processes across the world, maybe things like El Nino and IOD, but even other processes or other phenomena that can in turn impact monsoons. So one is more machine learning embedded in the physics as opposed to other way around. So what I was showing in those nowcasting models, short-term rainfall, it's physics embedded in deep generative models. Here we are talking about embedding machine learning within the physics to improve parameterization. And the other thing is using complex networks to, or network science and theory basically, to understand various kinds of relations that may exist across the world, and also see if we can use that for post-processing. So that's the kind of idea, that's the kind of focus that we have. And the eventual goal is to try to give the Indian monsoon mission some deliverables which they can embed in what they do.
Great, thank you.
And we'll be very happy to, by the way, to have a detailed discussion on that with whoever is interested, but also especially you, Professor, if you are, and talk about that more.
Yes, Sandeep?
Yeah, can you hear us now?
I can hear you now.
Good, very good. Yeah, I guess we don't seem to have any questions here right now. It's late at night here. So,
Yeah.
Thank you so much, Auroop. Maybe we should have a separate chat on this monsoon thing.
Absolutely. Monsoons and some of these weather things, and maybe if there are other things in river management or many of these other, networks kind of things. So Udit Bhatia, who is at IIT Gandhinagar now, he has been doing a lot of interesting work on concurrent extremes, floods, landslides, and what that means for roads. And then, there are others. So yes, happy to talk. I know it's very late over there. But I saw that this session is recorded. So if you have any questions or anything else, in general, just let me know. I'll be happy to talk, and happy to introduce any of the students and postdocs with my students and postdocs here.
Thank you so much.